Let's talk about how we can use trigonometric ratios to solve real-world problems. Remember from our previous videos that we learned about sine, cosine, and tangent. Sine is the opposite over the hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We use SOHCAHTOA as a cute little way to help us remember which one is which. If we need to calculate a side length of a right triangle, we can use sine, cosine, or tangent to help us out. For example, in this diagram, I know that the measure of angle A is 35 degrees, and that the side adjacent to angle A is 10 meters long. So if I wanted to know the length of the side that's opposite from angle A, which is side BC, I could use tangent, because tangent is opposite over adjacent. I would write tangent of 35 degrees equals BC over 10, and to solve, I would multiply both sides by 10 to get my answer. In order to calculate an angle measure, we're going to need inverse trigonometry. For example, if I wanted to calculate the measure of angle A in this diagram, I can use the adjacent side of 10 and the opposite side of 7 and tangent to solve. The equation that I would write is tangent of angle A is equal to opposite over adjacent, which is 7 over 10. To solve, I would need to use inverse tangent. Taking the inverse tangent of both sides causes the tangent on the left to cancel out, so I just have A, and on the right I would end up with approximately 35 degrees. So let's see if we can apply these ideas to solve real-world problems. For example, let's say that we lean a 16-foot ladder against a wall so that the base of the ladder is 5 feet away from the wall. What is the angle created by the floor and the ladder? Well, the first thing you should do on any word problem is draw a picture. And since we're dealing with trigonometry, we know we need to draw a right triangle. On this right triangle, the hypotenuse, the slanted side, is this 16-foot ladder. So I'll go ahead and label that with 16. And it says that the base of the ladder, which is down here, is 5 feet away from the wall. Well, the vertical side must be the wall, because walls and floors are perpendicular to each other. So the length between the wall and the ladder's base is 5 feet. So what we're going to calculate is x, which is the measure of the angle created between the 5-foot side and the 16-foot side. In relationship to the angle that we're going to calculate, the 5-foot side is adjacent, and the 16-foot side is the hypotenuse. So since I have adjacent and hypotenuse, the trigonometric ratio that I need to use is cosine. So I'll use this equation, cosine of x is equal to 5/16. To solve, I need to take the inverse cosine of both sides, type that into the calculator, and you get an answer of about 71.8 degrees. Let's try another one. A logger in Alaska needs to measure the height of a spruce tree. He stands 75 feet away from the tree and measures the angle of elevation between the ground and the top of the tree to be 58 degrees. So how tall is the tree? So let's start out by drawing ourselves a diagram. The vertical side of this triangle is representing the spruce tree. And you could draw a little stick figure over here if you wanted to represent the logger. He's standing 45 feet away from the tree. So the distance between the tree and the guy that's going to cut the tree down is 45 feet. And it says that the angle of elevation between the ground and the top of the tree is 58 degrees. That's this angle right here. With angles of elevation, you always start at horizontal and then work your way up from there. You elevate. So starting from that 45-foot horizontal line, we look up 58 degrees. And we're going to use these measurements to calculate x, which is the height of the spruce tree. In relationship to the 58-degree angle, the 45-foot side is adjacent, and x is opposite. So since I am looking for opposite and adjacent, that means I need to use tangent. The tangent of 58 degrees would be equal to the opposite over the adjacent, x over 45. To solve, I'll multiply both sides by 45, and I find out that the spruce tree is about 72 feet tall. Next up we have Hector, and he's going to hang a flag on the front of his house. When he places the flagpole in its holder on the house, the angle created between the house and the pole is 28 degrees. So if the flagpole is 6 feet long, how far out from the house will the tip of the flagpole be? The triangle that we should draw this time is upside down compared to the other triangles that we've drawn in the previous examples. Because this diagonal side, the hypotenuse actually, is the flagpole, and the vertical side is the house. We're interested in the area between where the flagpole and the house meet. It says that the degree of the angle created between the house and the pole is 28 degrees, and it says that the flagpole is 6 feet long. And what we're going to find out is how far is the tip of the flagpole from the house. So how long is this measurement right here? In relationship to the 28-degree angle, x is opposite, and 6 is the hypotenuse. So I'm going to use sine to calculate x. Sine of 28 degrees is equal to opposite over hypotenuse. Multiply both sides by 6, and I get an answer of about 2.8 feet. An airplane is flying 6.5 miles above the Earth's surface. The pilot looks down at an island at an angle of depression of 23 degrees. How far away is the plane from the island horizontally? So let's draw our triangle to get started, and draw our airplane. It's flying along through the sky, and it's 6.5 miles above the Earth's surface. So that's like if you were to drop a straight line down from the plane, that would be 6.5 miles. It says that the pilot looks down at an island using an angle of depression of 23 degrees. Angle of depression is the opposite of the angle of elevation, but they have some things in common. Remember I said on the angle of elevation problem that you start at horizontal and work your way up. Well, the angle of depression is similar. You start at horizontal, but then you work your way down. If your angle of depression was 0 degrees, then you would just be looking straight across. But it says that he's looking at an angle of depression of 23 degrees. So from this horizontal line, he looks down 23 degrees. So 23 belongs right here. It's a common misconception that this is where you should put 23 degrees. But that would be if you were starting by looking straight down at the ocean and then looked up from there. And that's not what we're talking about. An angle of depression starts at horizontal and then you work your way down. So this angle should be 23 degrees. But that's not even an angle in the triangle that I'm going to try to solve. So why do I care about this number? Well, this line, the dotted line, the 0-degree angle, that would be the pilot looking straight, and the horizon, or the ocean, those lines are parallel to each other. Which means that this 23-degree angle and this angle right here are alternate interior angles. And alternate interior angles are congruent. So I know that this angle has to be 23 degrees as well. And the problem is asking us to calculate the distance from the plane to the island, which is over here at the tip of this triangle. How far are they apart horizontally? So that would be this measurement right here. In relationship to the 23-degree angle, x is adjacent and 6.5 is opposite. So I'm going to use tangent to solve. The tangent of 23 degrees is equal to 6.5 over x. I need to multiply both sides by x, and then divide both sides by the tangent of 23, and I find out that the plane is approximately 15.3 miles horizontally from the island. For our final problem, we're going to use trigonometry to calculate the perimeter of this trapezoid. Remember that the perimeter of a figure is the distance around the shape. And I only know one of the lengths, and it's not even the entire length. I just know this little piece right here is 59. But remember that this shape in the middle of the trapezoid is a rectangle, and opposite sides of rectangles are equal. So I would know that this length is 59 feet as well. Likewise, I would know that FB has to be 45 feet long because AE was 45 feet long. Okay, well I still have a lot of things that I need to solve for, so let's get to it. Let's solve for the length of AC first. In relationship to this 66-degree angle that we have given to us, AC is the hypotenuse and 45 feet is opposite. So I'm going to use sine to calculate the length of AC. Sine of 66 is equal to 45 over AC. Multiply both sides by AC, and then divide both sides by the sine of 66, and we get an answer of 49.3 feet for the length of AC. Next up, let's solve for the length of CE. In relationship again to the 66-degree angle, CE is adjacent, and 45 again is opposite. So since I have opposite and adjacent, I'm going to use tangent. The tangent of 66 degrees is equal to the opposite over the adjacent. Multiply both sides by CE, and divide both sides by the tangent of 66, and we get approximately 20 feet for the length of CE. Next, let's calculate the length of BD. In relationship to this 44-degree angle, BD is the hypotenuse, and this 45-foot side is the opposite. Opposite and hypotenuse is sine, so I'll write that the sine of 44 degrees is equal to 45 over BD. Multiply both sides by BD, divide both sides by sine of 44, and we find out that BD is about 64.8 feet long. And the last measurement that we need is the length of FD. FD in relationship to the 44-degree angle is adjacent, and 45 is opposite, which means I need to use tangent in order to calculate its length. So tangent of 44 is equal to 45 over FD, multiply both sides by FD, and divide by tangent of 44, and we find out that FD is 46.6 feet long. So to calculate the perimeter, I need to add up all of my sides. AC we calculated to be 49.3, AB we knew was 59 feet, BD we calculated to be 64.8 feet, and CD is the sum of CE, which is 20, EF, which was given as 59, and FD, which is 46.6. So if you add all those numbers together, you get your answer of 298.7 feet for the perimeter of this trapezoid. And that's all you need to know about using right triangle trigonometry to solve real-world problems. In our next lesson, we're going to learn how to use trigonometry to solve non-right triangles.